Alrighty then, let's keep moving. So, to remind you where we were and where we're going, we did projectile motion for a while, and that was basically every which way you could launch a marble in the air or launch something in the air. Well, now we're going to look at things that are moving in circles and only in circles. So, here we go. We are going to look at this idea, uniform circular motion. So if you have not done so already, definitely have notes out and write some important things down as we get to them in this video. You're going to get quite a bit of vocabulary and a good number of equations, so you're definitely going to need to write a lot of stuff down. But for now, let's talk about the idea. Uniform circular motion. You probably think, what the heck does that mean? Well, if you think about what all those words are individually, it kind of tells you what's happening. Uniform just means that something is constant. Circular is circles. Motion, things that are moving. So things that are constantly moving in circles is what we're going to look at. And here's our circle. So I'm going to be moving something. Basically, something is going to be traveling on the edge of this circle at a constant speed. And that's the big idea of what we're doing. So at that point, if we're moving clockwise, then what we have here is it's moving tangent to the circle at that point. And if it's going in a circle, then that means we have to be changing its direction constantly. And that means it's accelerating towards the middle of this circle at every single point. So it might be traveling right at this point to the right. We're accelerating towards the middle. If we look at another point along the edge of the circle, then we're going to be accelerating still towards the middle. So the reason why there's an acceleration here is the velocity is changing. So if the direction is changing, velocity is changing. So that means there has to be an acceleration. So at every single point, doesn't matter where, we're always accelerating towards the middle of the circle. And went a little too far. Okay, so the big idea, speed is constant, but velocity is not. And that's because the direction is changing. So if the direction is changing, there has to be an acceleration. And we're going to be able to define that soon. But we need to define a few other things first. So here are definitely some things you need to write down. So I'm going to be using some of these words in class. So I expect you guys to know kind of what they mean. Now, period is the first. So this is simply the time it takes to complete one rotation. So if I was, swinging something around in a circle, if it takes 3 seconds to go one rotation, then the period is 3 seconds. So the time it takes to go one rotation. And the frequency is the inverse of that. So it's how many rotations happen in a second. So those two are inversely related. So period is how long does it take to complete one rotation, and then frequency is how many rotations happen in a second. The next thing we need to define is angular velocity. So angular velocity is similar to what you know in terms of linear velocity, but instead of covering meters or inches or feet or miles, we're going to be covering degrees or radians or rotations. So it's how fast something is spinning, essentially. But more specifically, in terms of what units we'll be using, it's the amount of radians covered per second. So if we look at what we already know about linear velocity with that equation, it's how many meters are covered every second. So x over t. Our new symbol for angular velocity is this, and this is omega. Let me write out the rest of the equation. So, oh goodness, let me go back. Okay, that thing that looks like a W is not a W. That's actually omega. So we will be calling this omega. That's the symbol. And that represents angular velocity, just like V represents regular velocity. Okay, the other symbol on the right you may not recognize is called theta. So theta represents the number of radians. So this is the angle that it turns in. And it's not measured in degrees. Notice how I said radians. T is the same, that's time. So there's no such thing as angular time. Time is just time. And there is your first equation. Now I said before that the period and frequency are inversely related. Well, this is what they look like in an equation. So we're going to use those to define or to calculate speed in a different way. So first, we have to look at t, the period, that's measured in seconds. The frequency is the inverse, so it's 1/seconds, and that is defined as a hertz, or hertz, so Hz. So any frequency you hear, so if you're a musician, then you know about 440 hertz, so that's a frequency that you hear. That's the number of oscillations per second. So same thing here with circles, it's how many times something spins per second. And we're going to use both of those ideas to define speed in a new way. So remember, all it is distance over time. We just have different ways to explain time. Now, here's our circle. We've got an object moving in uniform circular motion, and it's moving in a circle of some radius r. The distance around a circle is just the circumference, which is 2 pi r. So the speed is just the circumference divided by the period. So the circumference is the distance around one circle. Capital T, the period, is just the time it takes to go one time around the circle. So the speed is 2 pi r over period. And period and frequency are inverse, so we can also write this equation in terms of frequency. Instead of 2 pi r over t, we'll have 2 pi r times frequency. Alright, now I'm going to rewrite these on the next page. So here's your next two equations. Two different ways to find speed of an object traveling in a circle. Those are your two ways to do it. The next question is, okay, what about acceleration? Well, in terms of around the circle, it's not speeding up in the direction that it's moving. So we're not going faster and faster in a circle, but we are accelerating, and we're always accelerating towards the middle of the circle. And there are two ways to calculate this, and I'm going to give them to you. So here are the two ways. I'm not going to derive these because it probably won't really help you too much, so I'm just going to give these equations to you. So it's speed squared over the radius, and another way to calculate it is radius times angular velocity squared. So two more equations. And remember, this is a special type of acceleration. It's the centripetal acceleration. So if we're talking about something going in a circle, it's the acceleration that always points towards the middle. That's the acceleration we're talking about. Alright, so here's our circle, and it's going to be rotating clockwise. So if we look at any point, it's going to be moving, whatever this object is, it'll be moving tangent, exactly tangent to the circle, and it'll accelerate towards the center every single time. So any point on that circle, we're going to accelerate towards the middle. So if there is an acceleration, there has to be a force. Alright, so yeah, so like we said, if there's an acceleration, then there has to be the force in the same direction. When we looked at projectile motion, we found that there's always the same acceleration straight down. And that means there's always the same force straight down. Well, in terms of circles, or uniform circular motion, we have an acceleration right towards the middle of the circle, and we have a force, both pointing towards the center of the circle. And that force is called centripetal force. This word centripetal, all it means is center seeking, so that just means it's always pointing towards the middle of the circle, and that's all it is. It's a very special case for force. So let me show you where this comes from. I will actually derive this and show you where it comes from. So if we look at what we already know about forces, masses, and acceleration, we know that the net force is just mass times acceleration. If I want a centripetal force, then it's mass times centripetal force, or centripetal acceleration. And we've got two different ways to define centripetal acceleration: v squared over r and r omega squared. So here's your next equation, or yet three equations, but they're all the same equation. So all of these are just the same equation written three different ways. So we have one way, a second way, and a third way. So they're all ways to calculate centripetal force. Alright, so now let's go. Let's do an example so we can see how we can actually calculate all this stuff. We have an object moving in uniform circular motion with these values. The radius is 2, the mass of that object is 1.5, and the period is 0.25 seconds. We're going to calculate every single other thing possible. We're going to find the frequency, we're going to find the angular velocity, we're going to find the linear velocity, or the speed, centripetal acceleration, and centripetal force. Alright, let's do these one by one. The frequency and period are inverses, so we just have to take the inverse of the period. So it's 4 Hertz. So that means this object is moving, it's traveling 4 rotations per second. So every second, that thing is going to spin 4 times. So check, we got one of those. What's the angular velocity? So how fast is it spinning in terms of radians and seconds? So remember, this angle here is not a distance here. This is to how many degrees or how many radians does this thing spin every second. So every rotation is just 2 pi radians, and the time is the period. So the time is 0.25 seconds. So our angular velocity can be calculated by dividing 0.25 seconds into 2 pi radians. So our angular velocity is 25 radians per second. So it goes 25 radians every second. So it spins that amount of angle every second. Alright, so we got that one. Now we want to find what is its speed, linear speed. We know one way to calculate this, 2 pi r divided by the period. And it's a simple plug and chug, and we get 50 meters per second. So pretty fast. This thing is spinning very quickly. And so there's our next value. So then we want, what is the centripetal acceleration? So how much is it accelerating towards the middle of that circle? Alright, remember there's 2 ways we can do this. And I'm going to do both and show you that it's the same number both times. So even though I didn't derive either of those equations, I will at least validate that they are true by both of them giving you the same answer. So first way is v squared over r. We just found the speed was 50. So I plug that in my equation and I get this acceleration, 1263. If I do it the other way, now I wrote 25 right here, but when I did this on the calculator, I carried out all of the extra digits to make sure that it was as accurate as possible, and you will get the same exact answer, 1263. So we didn't derive these, but we at least proved that they are equal to each other, so they're the same thing. Now the last part is, what's the force? So if this, let's say this is a slingshot, a very big slingshot of 2 meters. So this force right here, this would tell you the tension in the slingshot. Now this is not a very realistic example because I made up all the numbers, and but anyway, you can see how the math works. So our centripetal force is our mass times the acceleration we just figured out. So 1.5 kilograms times that, it'll give us that amount of force. So that's a lot of force right there. That's very heavy. This would be a very strong slingshot that could withstand almost 2,000 newtons of tension. But anyway, more realistic examples in class when we actually are going to do a lab where we figure out tensions in something that's spinning in a circle. But I think that is plenty for now. Let this sink in. If you missed any of the equations or missed the example, please go back and watch them again. There's a lot of vocabulary and a lot of equations in this video, and I don't want you to miss them. But we will definitely have more practice in class. So bring your questions to me when I see you next, and we're going to do some more physics.